Good evening, ladies and gentlemen. Thank you for joining us at the SAIEE Lightning Chapter launch, where we're empowering members with knowledge. I'd like to introduce you to the chairman of the SAIEE Lightning Chapter, Dr. Andreas Boutel. Andreas Boutel was born in Johannesburg and graduated with BSc Eng, MSc Eng, and PhD degrees in electrical engineering from Wits University. He is employed at Eskom and was previously employed at CBI Electric, low voltage. His technical interests include electrical distribution, insulation and safety, as well as lightning and surge protection. Dr. Boutel is a registered professional electrical engineer in South Africa, a chartered engineer in the UK, and a fellow of the SAIEE. He is the current chairperson of the SAIEE Lightning Chapter. I hand you over now to Andreas.
Good evening, everybody, and thank you, Minx, for that introduction. And welcome to the launch of the Lightning Chapter, the brand new Lightning Chapter of the SAIEE. Before we start, I would just like to take you through a few house rules. We've called them considerations. The first one, I believe, has been a problem in the past, and that is please ensure that your volume is turned up. Otherwise, you might think that the system is not working. The next one is please ensure that you have a stable internet connection. Again, that might affect the quality. If you are really battling, then it might be a good idea just to switch off the webcam feed of whoever happens to be presenting at the time. Then secondly, or thirdly rather, you are not able to chat with other attendees, but you are definitely encouraged to ask questions via the question panel, which by default is on the right-hand side of your screen. Next, for those of you who need it, but for everyone as a default, we will be sending a certificate of attendance for anyone who needs that for earning of CPD points. Next, please, Minx. And then the last 2 points are if you would like a copy of a particular presenter's slides, these will not be shared automatically. So please then contact Minx, who will forward the request to the respective presenter for consideration. Likewise, today will be recorded, but tomorrow will not be recorded. So those 2 points at the bottom are due to the presence of some sensitive information in some of the presentations. So let's move on to the agenda. Today we are very fortunate, firstly, to have a welcome by the President of the SAIEE, Professor Sunil Maharaj. Then we have 2 guest speakers, both from the early years of lightning research at the CSIR, Dr. Henry Geldenhuys and Dr. Andrew Erickson. Then we will be looking more at what's happening at the moment and what we can look forward to with respect to lightning research in this country with Professor Ian Jandrell. And finally, we will then be taking questions for all the presenters together. So the aim is then to finish at about 7:30. Tomorrow we'll also be aiming to finish at around the same time. There we have 3 keynotes. Firstly, from Dr. Hugh Hunt, who heads up the Johannesburg Lightning Research Lab. Secondly, by a forensic pathologist, Professor Ryan Blumenthal. And then finally by Ian McKechnie, who will be talking to us about holistic approaches to lightning protection. So it's a similar format, and then we will be again aiming to close at around 7:30 tomorrow evening as well. So about 2 hours on both evenings. Next slide, please. Yes, please, sorry, I didn't see the link at the bottom. Please just see the registration link in the side panel for day 2. We've had more registrations for today than we have had for tomorrow. So if any of you would like to register for the second day, then please follow the link for that. Right, let's talk about questions. As I said, please type the questions in the question panel. Please do it as you think of it. The reason being that we are dealing with the questions at the end. But please just indicate who the question is for so that we know at the end who to pose the question to. If we run out of time at the end to answer all the questions, we will try to send the answers to you via email, obviously minus any sensitive information, but we'll have to see what the volume of questions is, and I suspect we might have quite a few. Right, next please. Okay, so this is just a few opening remarks just about why we have a Lightning chapter, or why we have formed a Lightning chapter as the Institute. The first point is about serving the public. In other words, reducing the number of lightning-related deaths that we hear about regularly in this country and also from other countries. But obviously, we're focused on South Africa. Secondly, as a service to chapter members and also to institute members in terms of skills development, sharing knowledge, and all of that. Thirdly, then, as a service to the industry, to improve knowledge generally, to assist with standardization, just as examples, and finally as a service to the country. Now these four are all fairly well interlinked, I'm sure you will agree. All we're trying to do basically is be good corporate citizens as engineers, and to assist each other, assist the wider country with issues related to lightning. Next slide please, Minx. Okay, now we're talking about the further details of the chapter, and there's some good news on this slide. Obviously, all the details are in the fully approved, complete governance document, but membership is open to anybody who's interested in Lightning. You don't have to be an engineer, you can be an academic, you can be a manager, you can be anything basically. So the first piece of good news is that you do not need to be a member of the Institute to join the chapter. And the next piece of good news is that chapter membership is free. However, if you want to become a committee member of the chapter or an office bearer of the chapter, then you do need to be a member of the Institute. And then the last 2 points at the bottom. Okay, joining is very simple. There's a Google form, which you should see also in the chat box. And we're planning the first full chapter meeting next month. And by full, I mean we've got a committee and office bearers, some of them at the moment. But obviously, once we've now launched the chapter, we would like all members to join us for the first chapter meeting next month. So please, if you're interested in joining, please complete the Google form as soon as possible so that we can get those meeting details to everyone. Next slide, please, Minx. Okay, so I've jumped the gun just a little bit. The Google form should be in the chat box. I did check it earlier, it was there. And just to confirm, there's no cost to joining the chapter, and you do not need to be a member of the Institute to join the chapter. Obviously, we do encourage it. The Institute holds a lot of different events, and the more you can get involved, the better. So as I said, please complete the form as soon as possible so that we can get that appointment to all members in time for that 25th of May meeting. So that's the end of my story. It is now my absolute pleasure to welcome for a few words of introduction Professor Sunil Maharaj, who is the president of the SAIEE. Now, Sunil is a full professor in the Department of Electrical, Electronic and Computer Engineering, and also the Dean of the Faculty of Engineering, Built Environment and IT at the University of Pretoria. He has a combined experience of more than 32 years in the industry as a microwave and RF design engineer, an academic and a consultant. He holds a BSc in engineering, 2 MSc degrees and a PhD in engineering. He is a registered professional engineer in South Africa, a fellow of the South African Academy of Engineering, also a fellow of the SAIEE, and a senior member of the IEEE. I welcome you, Sunil, and hand over.
Thank you, Andreas. Good evening to all attendees, certainly our SAIE council members, our office bearers, our past presidents, and members at large, and of course, most importantly, our speakers for today and tomorrow. Good evening, welcome, and thank you very much for this launch of the Lightning chapter and having such august speakers this evening. Is really exciting. Myself not involved in power engineering or lightning, but very much into the telecom space. I'm very impressed and intrigued by the lineup of the speakers and the topics they chose, which is very topical and of course of great interest to the broader fraternity of electrical engineers and of course the public at large. So certainly I'd like to thank Dr. Andreas Vittel and his team for starting this chapter and of course taking it forward with such a exciting event. And looking at the number of members and attendees we have this evening, it certainly shows that there's a great interest out there. And of course, I'd like to thank also the organizers for putting this together and the marketing team and of course the people that put the technical program together and of course those that helped with the logistics today. I think Andreas mentioned about the SAIE and of course serving the public and serving the industry and serving the profession. And today was also a very exciting day because today one of our past presidents, Mr. Andres Mpila Mtetwa, received the Chancellor's Medal for his contribution to the profession and society at large in electrical engineering. And we are really passing our congratulations to him. And of course, being a past president of the SAIE and also involved in council quite actively, we'd like to wish him well and thank him for his distinguished service. So from my side, it's pretty simple. I'd like to welcome everybody. Thank you for joining us today. And we hope that we can all add our bits to helping the SAIE serving the profession and the country at large, and of course the African continent much more than we currently are. And certainly I think with all our contributions and efforts, we can really have a greater impact on society. And Andreas, thank you very much for putting this together, and I wish you well in the deliberations. And I'm certainly looking forward to further events as precursors, as forward looking and taking what we have today and tomorrow forward to the industry and of course to students who are our future engineers and future leaders. We need to excite them and get them more involved so that they become an active part of this community going forward. Thank you, and I'll pass you over to Andreas.
Thank you, Sunil, for those very encouraging words of welcome. And just to add on to what you've said, we now have over 100 people who have joined the session, which is really encouraging for today, for tomorrow, for the lightning protection and lightning interest fraternity generally. Let me also join Sunil in thanking all the presenters today and tomorrow, and secondly, the current members of the chapter committee who have been so helpful in organizing today, especially Dr. Hugh Hunt, who is the vice chair and who we will be hearing from tomorrow. Right, our first guest speaker or guest speakers are Dr. Henry Geldenhuys and Dr. Andrew Erickson, who many years ago worked for the CSIR. I will be introducing Dr. Geldenhuys, who will then in turn introduce Dr. Erickson. Now, Henry has been working in the power industry in this country for close to 40 years. I myself have had the pleasure of working with him for well over 10 years at Eskom. He is currently employed as a corporate specialist in the distribution division of Eskom. And as you can imagine, large utilities can be complex organizations that require a lot of thought, a lot of homework when it comes to making certain decisions, especially when it comes to technology. And Henry often deals with the issues of business integration and assists in dealing with the the broad impacts of certain technology decisions. The subject matters that he deals with is a wide range, dealing with things such as the integration of renewable energy, smart grids, insulation coordination, design of networks, safety, and of course, lightning protection. He is particularly an expert on medium voltage system insulation design, as well as issues dealing with low voltage systems. And his focus is often on safety related aspects, as well as other design issues. He has extensive experience in power system loading as well at the medium and low voltage levels. It's an absolute pleasure to welcome you, Henry, and I look forward to your presentation.
And Andreas, can I confirm, is my screen now, okay, I've clicked it and is my screen displaying? My slide screen, is that coming through?
No, go on display settings in the middle top.
Show screen. Is that the one?
No, it's display settings in the middle top of your, the one that shows your presenter view.
Sure.
I don't see your mouse, so you must work on the other screen. There we go. Okay, I just saw your mouse.
Yeah.
Okay. Left-hand side, top middle says display settings.
I'm still not with you, Minx.
Okay, move to the other screen where I can see your mouse. I'll tell you when I see your mouse.
Where do you see my mouse?
I don't see it.
I can see it.
Yeah, we see the wrong screen. So move over so your mouse goes onto your other screen. There we go.
I've got other. Okay. Let me go out of my presentation mode. I'm now completely out of my presentation mode.
Okay. Click on your presentation mode again.
This is PowerPoint you're talking about.
Yes. Click on that. Yeah, click on that. Okay, now we're still sitting with the same problem, obviously. So, okay, wherever your mouse is now, just move your mouse so I can see it. Okay, I don't see it, so move over to the other screen. Okay, there we go. Go left. Yeah, that. Click there, display settings, swap.
Okay.
There we go. Click on that. No, top one. There we go.
Can you see it?
Yes, now we see in black the CSIR Lightning and High Voltage Research Program.
That's right. And my camera is still on.
Yes, continue.
Okay, I can't see my camera. There it is. But that's at the top now. So, okay. Great. Excellent. Ladies and gentlemen, thank you. Sorry for that little interruption. Engineers sometimes need to be trained by excellent PR people like Minx. Minx, thanks for that. It is my pleasure this evening to firstly congratulate the Minx. Sorry, I can't see my own slides now. I've
okay,
only
at the
got
bottom is the arrow. Yes, there. No, there. There we go.
Yeah, but I can't see my slide notes. I have to see my slide notes.
Okay, I see what you said.
Come on.
Can you not pull that over to your other screen?
I was seeing all three settings on the same screen. I've got 3 screens in front of me, and all of them were displaying the same. Okay, so can you still not see it?
No, now we see just your PowerPoint presentation with your notes. So move this to the other, yes, and now move your actual normal one with the notes to the other screen.
Okay, but I'm duplicating everything into the same screen now. So, okay, I think I understand now what to do. Right. Display what you want me to really. Minx, can I send? Andreas, do you have my slides? Can you just back it up?
Henry, what would you like me to do? To present them? And you talk?
Yeah, possibly.
I can try. I'm pulling it up now, and I can present. Minx,
Okay,
can you make me presenter?
Yes, I will.
Give me a sec to just, yep. Okay, now this is all I can see, Henry, so you must just tell me when to move on, please.
You now past where we want to be. Just go back on the slides. You are.
Oh, that's all I've got. Starts with CSR Lightning and High Voltage Research Program.
Oh, okay, but I'm not seeing your screen now, so.
Oh, that's
okay.
not...
Now I can see it. Thank you. My screen is now organized. Thank you.
Okay.
Good. My apologies for that. At least I can see my own screen now. Andreas, just a word of congratulations to your Lightning chapter that you guys has got off the ground. For those of you that don't know Andreas, you must note on his surname being Beutel, if I pronounce it correctly, Andreas, which means from German origin. And my experience with Andreas is that he's extremely organized. When he tells you he's going to do something, then it's going to happen. And so this chapter is really kicking off with an excellent chairman. And we're looking forward to you guys serving the SAIEE and carrying the message of lightning and lightning protection and all of those good things into our membership and widening the interest of even medical doctors, Ryan, into the SAIEE. Now, I'm going to introduce you just now to Dr. Andrew Erickson. And the reason why I insisted that I wanted to introduce Andrew is that I need to give you a little bit of more secretive background to Andrew. In my very, very early days as an engineer, he was my boss, and I still regard him as my primary mentor in engineering life. And I'll talk about that a little bit more later. But you know that the typical stereotype of engineers are awkward introverts that really don't know much about social skills. And we want to possibly towards the end of this evening's discussion delve a little bit into the wider issues around engineering and your career as you go forward, as a little bit of a wetner, appetite wetner to the young engineers in terms of their career and going forward in their careers. The fact about engineers is that they operate in an environment where successful outcomes always requires an effective teamwork. There is no engineering which is done by a single individual. It is done by big teams of people that need to engage with one another in an effective way. And the leadership of those teams is critical in our environment. We will be discussing a lot of deep technical engineering tonight, but towards the end, I would like to see whether we can entice Dr. Erickson in talking a little bit about his career as well. Andrew, if you can, Andreas, if you can just open up the next part of the slides. Click twice. So go again. You can click again. Dr. Erickson has been an engineer at grassroots level, but he's also risen through the ranks of ABB to the top of the group. And the later part of his life, he has played a very important role in change leadership, which is so important to our current environments that we work in. Next slide, please, Andreas. Now, although Dr. Erickson has lived for the past 30 years in Switzerland, Andrew can be regarded as a true son of Africa. He was born in Tanzania, in Arusha. And Arusha politically is, for those of you that don't know, in Tanzania, a important political center in northeast Africa. He moved with his parents down to South Africa at a later stage, and he studied at KZN University, where he obtained his MSc and his PhD. Andrew, in his career, was not only at the CSIR, but he started a consulting practice at one stage. He came back to the CSIR as assistant director of the engineering laboratories of NERI, the National Electrical Engineering Research Institute of the CSIR. And that was in the years of 1984 and 85. He did a lot of groundbreaking research work that we're going to talk about this evening. Much of that work is still leading the thinking in SAIEE and the IEEE in many respects. And he was instrumental in building the team that executed a lot of important lightning research work in those days. Next slide, please, Andreas. For the record, there is more to his CV, which I'm not going to read this evening, other than just again observing that he spent 16 years at ABB. In his next phase of his career, he did consulting, advising large corporates with respect to adapting to the changing world. It is my honor and privilege this evening, ladies and gentlemen, to introduce you to Andrew Erickson. Andrew, can you give us a little bit more background about those early days? What led you into the lightning research arena? What was it like in those days? Who were the people that brought you into this environment?
Well, thank you, Henry. Maybe we could jump to the next slide, whoever's driving them. And I also would like to congratulate the Institute and the leadership team that you've taken the step to form a chapter in lightning. I have to say, if I think back to when we were active in South Africa and in the SAIEE, where I was also a member of the council for some years, we never thought of forming any kind of special group or interest group or chapter. So we were obviously a bit stupid back then. And I really congratulate you on taking this step, because South Africa has had an important history and is continuing to be an important player in advancing lightning knowledge. And I wanted to bring this slide because the lightning research in South Africa didn't start just out of the blue. There was an important background of it, apart from the history of early people like Basil Shanland and Malan. One of the very key individuals behind all of this was Dr. Ralph Anderson, himself a president of the SAIEE about 30, 40 years ago. But Ralph was an engineer who was instrumental in launching everything that we did at the CSIR. He started himself in the former Southern Rhodesia, now Zimbabwe. He worked for the utility there, and already back in the late 1940s, he was writing award-winning research papers on dealing with the practical problems of lightning in power systems. He was recruited to the CSIR when the Institute for Electrical Engineering was just getting off the ground. And he was recruited in 1965 to start an electric power division. And he's the father of all of this. And in the very early 1970s, he was also a member of the SAIEE Lightning Working Group, which was an international group of engineers and scientists and academics who themselves were trying to advance knowledge and application and research on lightning. And he, in turn, through that committee, got to know a lot of other key players. And that's why I wanted to have this slide, because the key players here are Professor Carl Berger in Switzerland, who in the 1950s to 1960s made pioneering lightning measurements on a little mountain in Switzerland. He captured the current impulse during strikes. He captured the actual progression of leaders downward and upward. And he wrote very, very important fundamental papers which have been at the background of engineering application ever since. He also happened to be the most difficult external examiner in my PhD thesis. And then we had Dr. Goldie, who wrote probably one of the seminal books on lightning protection, also a close contact to Ralph Anderson, and with him, Ted Allibone, who is a really unknown name. Most people are not aware of his work on lightning research. He actually was a colleague to Basil Schonland, and he himself was a partner and mentor to at least 3 Nobel Prize winners in physics. In particle physics, he worked with Ernest Rutherford, the Nobel Prize winner in the whole beginnings of particle physics. And he provided all the high voltage apparatus to a very nervous Ernest Rutherford in his early days of splitting the atom. Now, these 3 gentlemen, Ralph Anderson, Goldie, Allibone, and the 4th, Carl Berger, I met once in Paris when Ralph was just starting the working group in lightning. And he brought me into a room as part of his process to encourage me to start getting interested in lightning research. And these 4 gentlemen, not yet John Anderson, but the other 4, were all sitting in this room with Ralph together. And to my surprise, they were all very small men. Ralph himself is not a large man. But the other 3, Allibone, Goldie, and Berger, were even smaller. And I have to admit, my very first thought when I walked into this room and met all these eminent but very small men was, is this a prerequisite? Is this a requirement to start in lightning, that I have to be small or be ready to get smaller? And that disturbed me slightly until I met the last man on this slide, which is John Anderson from the United States. He's a giant of a man. He's at his prime, he was approaching almost 2 meters tall. And he was one of the primary engineers in General Electric in the United States. And he already was making lightning current measurements on the Empire State Building in 1946. And he's been a father in many high voltage studies involved in transmission up to 1500 kilovolt transmission. He's one of the first engineers behind lightning surge arresters and their application in transmission lines. And that illustrates another point which is behind everything we did at CSR. Is all these gentlemen, although they were eminent research people, were also practical engineers. And that's been a fundamental aspect of all our lightning work at CSR, is this bridge between research and application and solving problems in real life in industry. Next slide, please. This is just a quick summary of the various projects that were in progress in various stages at the CSR. As this work started, it started with the Lightning Flash Counter program, and it was a very tiny team of people. And it gradually grew as we got into the further projects. And we'll touch on these projects briefly, Henry and I, as we go forward. Next one. Next slide, please. And this slide is just to illustrate that there was some logic to why we did what we did and how we progressed in what we did. The whole program started with the lightning flash counters on the left, And the objective here was to measure the ground flash density, to find out how much lightning do we actually have in South Africa, and where is it, and when is it? So those were the questions that we wanted to be answered. And it's a fundamental need if you're doing any engineering problem solving lightning protection issues, you need to know how much and where. And the second project which emerged out of that was the 11 kV test line project with Eskom, where we wanted to know what does lightning do in a normal, practical distribution line. And the third project came out of that quite soon after that, which was the lightning tower itself, where we wanted to know what are the characteristics of lightning, especially the current. What is the energy in that current? How many strikes? How much energy is in it? And how does the striking process itself happen? Why does lightning pick on something to strike and not something else? What is that process? How are those decisions taken during the physics of that process? And then another important aspect of all we were doing there is everything else was done in parallel with contract work for South African industry, dealing with problems in networks, in factories, in power systems generally. And as time progressed, we got quite a lot of cross linkage between the research and the application to solving problems later on. For example, the coal mine industry was having problems with lightning disturbances underground. Those came in as contract inquiries, and Henry was one of the people that really took that work further. In dealing with lightning measurements and learning how to survive in an engineering environment when lightning is striking you and your equipment, we had to understand how to protect our own instrumentation. And so this led to applications in many contracts in protecting electronic systems and grounding of equipment, which again were fields that Henry took over and took further. And we even got a contract from the one of the Brazilian utilities to build a lightning research tower and project for them, which was an absolute twin of what we did in South Africa. So this parallel relationship between research, answering questions, solving problems, and then applying that in contracts where industry was paying for the information was a powerful learning process for all of us as engineers. And this work led ultimately to a broad linkage between what we had learned from lightning and how it affects transmission and distribution systems into the design of transmission networks and substations. It happened to be the time when Eskom was studying what was needed for 800 kV transmission, and we worked closely with Eskom, especially people like Chris van der Merwe, in developing insulation coordination studies for those future 800 kV systems and for protection of the transmission lines, the design of the shielding, the design of the grounding, and the protection of the substations. And it was ultimately through that work that the overseas companies like the then Brown Boveri learned about what was happening in South Africa. They wanted to sell equipment to Eskom, of course, for 800 kV, and they recruited me to join them to take the insulation coordination work further inside ABB. So that's just a brief timeline and logical sort of flow of how the work developed and followed into a broad program of application. Next one, Henry.
Andrew, your departure to ABB was one of my first professional shocks. I was happily being led by a guy that knew what was going on, and all of a sudden he buggered off to Switzerland. So thanks for doing that to me. I appreciate that.
Well, I have had no problems with that, Henry. You took it forward very powerfully, and it's very visible in the papers and reports that you developed and all the results that followed through. So well done to you and the team that continued.
Just on the theme of people being engineers and teams and so on, you know, it takes an effort of a team. Sometimes the boss disappears, and there's always people underneath you that you should never underestimate and give opportunities to. And one of the things that you did to me that you probably completely forgot was that almost my first week at the CSIR, you sent me to an EMI EMC course. Can you remember that?
Yes.
Run by a guy by the name of Don White.
Yes.
Now, I've never worked in EMC EMI, but that course that you've sent me on has served me so well throughout my career that it is incredible. So, you know, this kind of teamwork and I had the opportunity to watch you as a skilled operator. You were not one of those mentors which said, Henry, now let's plan your career. You never did that. You were too busy to do your own thing. But I had the opportunity to watch a really, really excellent, skilled engineer doing his thing. And that's probably the best way to ever learn.
Mm-hmm. Agreed, yeah.
So that leads us now to the flash counter project, and you were arriving at the CSIR at the early stages of the flash counter project. Is that correct?
Yes, this project was just getting off the ground at the time. They had just developed the basic lightning flash counter, and I joined at the time they were starting to install these counters all around the country. In fact, I took advantage of that because I had a property in the Drakensberg. I was a very mountaineer at that time, and I took two of these counters, one to put it on my property and another one on top of a mountain in Lesotho. And if you look at the map on the right, there's a little high flash density area right on the corner of Lesotho, on the eastern corner of Lesotho. And that comes from the counters that we positioned in that area. And so I had the excuse occasionally to drive to my property and to the mountain in Lesotho and go and take readings of the counter.
Very nice. Just by the way, the photograph of the flash counter I took in Singwetsi Rest Camp of the Kruger Park last year. And 35 years after this project has ended, this flash counter is still respected, standing there all alone, doing nothing for the last 35 years, I guess. That's quite funny.
Yeah.
And in fact, there's another one in the Kruger Park. So the lions and the buffalo and the elephants are protecting us very effectively.
So this work led to probably what was the world's first reasonably meaningful map of lightning flash density right across the country, and it highlighted the very broad range of diversity in the intensity or the density of lightning across the country. And as you know, much of South African industry tends to be concentrated in those areas of higher lightning flash density, and reinforce the need to understand more about lightning itself. Okay, next one. Yeah, this was a picture that I was very happy Henry could find, because it really illustrated the very basic instrumentation that we worked with in those early days. This was the 360-degree mirror that was used with a camera above it to photograph the direction of lightning. And there was a network of such cameras around the Pretoria Highveld area, all synchronized in time, which was given by those little counters to the right of the camera itself. And the camera was a very expensive electromechanical robot camera, which looked down on that mirror. And the best part of all was the mirror was a Volkswagen hubcap, and proved to be a very effective 360-degree mirror. So each time there was a strike, the camera would capture that, and as shown on the right-hand picture, you can see on a 360-degree profile where that flash went to ground. And by synchronizing this from multiple stations, you could determine how far away the flash was, and in that way also correlate that with whether a lightning flash counter operated or not, and so thereby determine the range, the effective range of the flash counter. And there was a process of running all of this kind of stuff for 5 years before that map could even start to be formed. Okay. Yeah. Henry obviously felt sympathetic that we had to work with fairly simple equipment back in those days. And one of the reasons I got drawn into the lightning work at all was I liked the robot camera. One of the first industrial contract projects that I had to take on was with the South African Railways, who were being disturbed by surges, high voltage surges in the overhead catenary system, damaging equipment on the trains. And they didn't know whether it was coming, whether it was lightning or switching surges or some other problems. And since my role initially had been to build up high voltage work, we had developed high voltage potential dividers to measure over voltage surges. We installed those on the South African Railways line, and then we needed a way to capture whatever surges occurred automatically on the oscilloscope. And so we thought of using these robot cameras in a horizontal mode and use them to automatically capture surges. The only point I would make here is this oscilloscope is much more modern than the ones we started with back then, which is now almost 50 years ago.
Yeah, at the time that I joined, Andrew, the digital wrist watches came onto the scene, and what I've pasted there into the picture is what was done also at the time by Dave Meal, was to, in that photograph, you will also have a digital wristwatch, which gave us what, about 1 or 2 seconds per month accuracy, something like that, in synchronizing whatever was going on in the project. So the modern GPS time synchronization didn't exist in those days, but you guys were doing about 1 second or so per month, I guess.
Yeah. Okay. Yeah, it was also the time, of course, of crude television and recorders. I was interested to see that you found this particular camera in some digital museum. But at the time, we were very proud of starting using television cameras. And on the Lightning Research Tower itself, we had to find silicon diode type cameras to get the needed light sensitivity and the ability to capture very, very short events. These are very expensive and rather crude, and of course everything was captured on a recorder, and so we had staff, very diligent and loyal staff, including our secretaries, who would study many thousands of meters and images to gradually build up data for us. Thank you. Yeah, this is more or less the time when Henry came in and took over the work, but we had advanced our lightning research work on the tower enough and had proven that things were basically working enough that we got a budget increase from our director and were able to buy the very first nuclear oscilloscope, which made life a lot easier, except for capturing the image itself. And Henry, maybe you can just mention the use of the Polaroid camera.
Yeah, the problem in those days were, like now, we will just simply transfer the data into an Excel file and make a picture out of it and a PowerPoint and whatever. That didn't exist at the time. So although we could record 8 digital images, getting it into a report still required a Polaroid camera like the one that you see there in the picture, and you will stick that Polaroid picture then into the report that you were doing. And many of the test line reports were done with those photographs.
Okay.
Andreas, next one.
So this was maybe our headline project, and this was initiated again by Ralph Anderson. By this time, we'd had a lot of experience capturing overvoltage surges on the railway system, in various industrial networks, switching surges, and getting to know how to use cameras and oscilloscopes properly. And Ralph raised the question, how do we know that the lightning that occurs in South Africa is similar to the lightning that Professor Berger had measured in Switzerland or John Anderson had measured on the Empire State Building? These are the two main sets of data that existed in the world, apart from a little bit of data from Russia and Eastern Europe at the time. And so that was the question. And SAIEE and the international engineering community needed to know is, can we use one standard distribution of lightning current amplitudes for engineering design purposes? Or do we have to pay attention to variations in the severity of lightning around the world? And so Ralph had this idea that we should set up our own lightning tower and measure direct strikes, and in this way try and answer that question by collecting enough data to get a meaningful distribution. And at the same time, he was doing his own theoretical work on how the lightning strike and how the leader progresses from the cloud to the ground, and he was modeling that. And so the question was also raised, how does lightning strike? What determines that decision taking? People like Berger had measured already with high-speed cameras and seen how the leader comes down from the cloud, but there was no real measurement done of the actual decision point of strike or not. And so we set up, apart from the tower, we set up two cameras more or less at right angles to each other and a few kilometers away. One was on top of my house, together with television cameras. These were again automatic robot cameras, filming the tower and the sky above the tower through a grid, a metal grid, where we could impose a coordinate system onto the geometry of the photograph. And by doing this simultaneously and time tagging these photographs, we could capture and build up a 3D image of the lightning in a mathematical model. And our aim out of this was to try and see at what point in its approach to the tower did the leader, as it were, take the decision to strike the tower or not. And that was how we studied the striking process and the striking distance. The tower project itself was a major challenge for the team because we had nobody else to tell us how to do this. The South African Post Office lent us one of their survey towers. I'm not sure we ever gave it back. Maybe, Henry, you still have a bill from the South African Post Office to pay there. But they lent it to us, and they used it for surveying the microwave routes. And we wanted to build this close to the laboratories at the CSR, so we built it on a hill, on a kopje, on the CSI property, so we could get to it quickly to solve problems. We built it on an insulating platform and supported it with insulating ropes, so the lightning current was really confined to the tower. And by insulating at the bottom, we could introduce a shunt or impulse transformers, spark gaps, and whatever other measuring devices we wanted there. But all of that we had to design, the mechanical engineering, the wind strength, the foundations for the ropes, and we had to learn how to set up instrumentation right next to something being struck by lightning. So we learned a lot about grounding, shielding, protection. We had to build an insulated power supply to bring power to the site, because the CSR was nervous that we might blow up the rest of the site. And because of the insulated base, we even had to put an insulated power supply across the insulators to be able to power the aircraft warning lights on the mast. And as an ex-mountaineer, my job included climbing the tower to change the light bulbs. So we had a lot of fun and a lot of painful learning in doing all of this. And it took us a long time to get to the point where we were able to measure the first strikes and capture the first lightning currents. And during those early storms, we had the experience of capturing a strike, capturing the impulse currents, and then about 10 minutes later, watching the tower fall over, which was a bit disillusioning for everybody. And the tower landed on the hut where all our instrumentation was, which also didn't help the matter very much. And we learned out of this that the ropes that the post office had told us to use turned out to be fiberglass rods, which the fiberglass itself delaminated during the high wind vibrations. And with rain entering those cracks, and then when the lightning striking the tower, we get some discharge into the rods and they fractured, and so the tower fell. So we had to solve the problem also finding suitable ropes that were insulating that would not be affected in the same way. So as engineers, we learned a lot of practical problem solving along the way. Okay.
That's excellent, Andrew. We've got about 10 minutes to go to the end of the seminar.
Okay, then
so
move on.
we need to move along a little bit.
Okay, let's take the next one.
The next slide is about the base of the tower. If you can just very briefly share with us some of the, Andreas, the next slide, please. Some of the details of the tower's bottom, the field mills, and so on, the instrumentation.
Okay, these are actually photographs from the project in Brazil, and they absolutely copied the design. They took my drawings of the mechanical structure and rebuilt it, put it on similar post insulators. They had a similar ball joint to take away the mechanical stresses into the insulators, and they set up similar instrumentation. And the CSR got itself here a R500,000 contract for doing all of this, which was at the time was a lot of money, and we were all very pleased with ourselves. So it gives you some sense of what it looked like at the bottom. Okay.
I just got permission from the German chairman that we have a few minutes more, Andrew. So I think we can take a bit more time.
All right.
The bottom of the tower, if I can just talk about that a little bit. These funny things that you see there, these white tubes, is stuff that Andrew delegated to me as a project. I had to calibrate these things, and for those of you that don't know what you're looking at, you see these little black dots. They are what we call magnetic links. It is little tubes with essentially a hard magnetic material inside, which if a lightning strike current goes down the center tube in the center of the conductor, the magnetic field that is generated leaves the remnants in those links, which is proportional to the peak of the current that came down the center conductor. And so one of the things that Andrew meticulously did was, if this fell and that fell and that fell and that fell, there is somehow some record of what happened. So that, for example, there's spar gaps at the bottom of the tower, and if everything fails, you will see a etching of the spar gap at the bottom of the tower. In addition to that, we will have a recording of the peak current that flowed in this conductor, somehow recorded in these magnetic links, and they're spaced like they are because of the saturation that takes place. If they're too close and the current is too high, they will saturate, etc. So that is how some of that worked, and that, for example, the calibration there, Andrew, was only possible because of the HV lab that you developed at the same time.
Yeah.
The other part of what you see in the photographs here is the field mill as well as the flash counter. And the other job that you gave me was the lightning warning system. Remember, we didn't even spoke about the warning system.
Yeah, yeah.
I fondly remember one Christmas Eve sitting at the observation room at the CSR, recording the time to thunder. And kind of calibrating the warning unit in doing so. But that was another aspect that I'm sure you can remember.
Yeah.
And even the understanding of the relationship between electric field. The field mill is a meter that measures DC electric field. The flash counter measures the change in electric field. And through the work that you've done in your thesis, for example, you've run a correlation between the probability of having lightning and very high fields. Can you remember that?
Yes, that was an important thing to clarify. Yeah.
Yeah, and the answer in that, just tell us a little bit about that.
Well, the aim was to see if there was a relationship between the intensity of the electric field that built up on near the ground as the lightning approached, because the decision to strike depends on the electric field and its enhancement at the top of the tower, and the initiation of a connecting leader from that point And so we studied electric fields for a number of years in relation to storms and proximity to lightning flashes. And in this way, we built up a lot of basic knowledge about the movement of storms and the approach of lightning, and were able to design a lightning warning instrument which applied a certain logic that came out of our data and later found its application in the coal mines as one of the warning tools in the early stages to avoid people being underground if lightning was approaching. It was also something that won a patent in the United States Patent Office, which we were quite pleased with.
Yeah, and the punchline that I thought you will refer to is that there's not a too strong correlation between the static electric field and the risk of lightning.
No,
it was one of the learnings that came out of your work.
For sure, if lightning's coming, there will be some electric field on the ground, near the ground too.
But the presence of the field alone is not a guarantee that lightning will occur.
Yeah.
So that's why flash counters were used as the primary sensing device in that warning device. Andreas, let's move on. I think that's just a different view of the Kashimbo Tower. These photographs were taken. I had the opportunity to visit the site after our installation initially in 2007 again, when there was an ICPL conference in Brazil, and I used the opportunity to go and visit them. It was a little bit dormant at the time, but I believe that the research is now picked up again, and I'm sure we will hear more about that again tomorrow night. Andreas, you can move on. Andrew, if you want to kick off this one on the test line.
Yes, I mentioned briefly the test line, which was a joint project with Eskom to investigate lightning disturbances in a distribution line. There were already plenty of mathematical theories about the induction of overvoltages into lines when lightning strikes nearby. And the objective here was to set up measurements, again applying our competence in measuring overvoltages, using robot cameras on oscilloscopes, using lightning counters to trigger equipment, and using cameras to also photograph the lightning. And over a period of years, we collected a large amount of data from this test line, which is about 10 kilometers long. And the picture on the right shows a typical induced surge, where you see it's similar in shape on all three phases, which is characteristic of a small distribution line. And it was a very interesting project for us. We learned a lot out of it, and Henry and his team took the research much further than we did. But it was also a fun project for people like Dave Meal, who was our senior technician and extremely important in helping us do all these measurements, because he and I would go out here quite regularly to collect the data from the caravan. And we would generally have a little braai on a shovel that we had in the grounding systems.
I remember those days.
In the bowl of the shovel, sometimes have a beer, and then we'd go back to the office and present the data.
Absolutely.
So it was one of the fun parts of doing research out in the veld.
Just for the sake of interest, two things around that. Those were the days that you could still drink beer while you were working.
I'm not sure we were like
today.
We were working hard enough.
Andrew, very importantly, for me, one of the key things that you mentioned was that your work and our work were based on measurement.
Yes.
I need to tell you a little story, and it's a very dry humor story, which I had the arrogance of telling in the international conference on lightning protection in Graz. I think it was in 1988. I was listening to all these fancy professors telling us about the theory of lightning. So when it was my turn to present, I stood up and I said, I need to tell you a story first. And I didn't explain to them that it's dry humor, because it's hard to laugh at the joke, but it applied so much to the case. And the story is about the Acropolis in Athens, and there was these philosophers that were arguing about how many teeth a horse has got. And the one guy said, no man, it must have one tooth, because you must at least have one tooth. Another guy said, no man, can't be the case. It must at least have two teeth, otherwise you can't chew properly. And so this thing went around and around and around, and then one guy stood up and said, guys, man, let's just go and count it. And everybody else was really furious with this guy. And that's the simple little story. Dry humor. And I said, Mr. Chairman, I have to apologize. I can only share with you some measurements that we've done. In this environment where everybody else was telling us about the theory of lightning and how the physics, how the mathematics were working. And it is so critical in terms of the work that was done at the CSIR, because none of our work was, I don't want to call it highly mathematical and so on, because your models did involve a lot of maths at the same time, or some maths. But it was calibrated with real measurement. It was reflective of real measurement, and I think that's the critical element. Also, in the measurements of the lightning on the test line, there were lots of people modeling that. But actually, our models turns out to be, compared to real measurements, were unknown. And that's the big contribution that the work that you guys have started, that the CSIR made to the international environment. Andreas, if we can go on to the next slide. There is a little bit more, some of the results from the test line, and if you go to the next slide, the test line, yeah, okay. Let me just hand back to you, Andrew, on this slide, and then I'm going to just talk about the publication on the test line.
Okay, this slide in a way consolidates quite a lot of data. Henry just mentioned the key fact that the work in those days was aimed at measuring what was happening, answering questions about real-life lightning and what it does and how often and how big. And by combining many years of data of strikes to the tower, of different amplitude of current, combining that data with other data from other parts of the world, from Professor Berger, John Anderson, the Russians, the Eastern Europeans, the Canadians later, combining that also with the data on strikes to the test line, which is a much smaller structure and a more realistic structure than our towers, we were gradually able to build up some correlations between the height of a structure and the so-called attractive radius, the distance over which it collects strikes. And although it may look like simple data and simple correlations, it was a massive amount of work that consolidated this and finally found its way into a number of the international standards used by SIGRE or developed within the IEEE, and is still used today partly as a very basic estimate of the attractiveness of structures in terms of the number of strikes. So if you combine ground flash density with this kind of relationship, you can make a rough estimate of how likely is it going to be that something will be struck. And by including the data on lightning current measurements, you can then make a probability on how likely is it to be struck by a certain amplitude of current.
Excellent. Andreas, next slide. Not long after, but after Dr. Erickson left the CSIR, the work on the test line did continue, and although the CSIR around about 1988, Andrew made a major change in its strategic direction, and so much of the we had budgets for doing fundamental research and applied research, but there was a very substantial change in the direction of the CSIR around 1988 or so, a little bit later than that. But most importantly, the work of the test line, as well as the work that was done at the CSR and some other people, were combined in this document that you see here. It's a publication which was published by this institute. You can see at the bottom it says the South African Institute of Electrical Engineers, and I think if Garda scratches around, there's still a couple of copies of these in the library somewhere. But it set the basis for the protection of MV lines, and Eskom has used this as a guideline ever since those days. Now, more importantly, the work has continued, and in the generation of knowledge and the progression of knowledge, if anybody asks me where does the 300 kV BIL Andrew comes from, I actually blame you for it, because you were the. I distinctly remember one day asking you, but how did you arrive at 300 kV? And you had the explanation. I don't know if you can remember that.
I can remember the explanation.
Okay, great. Just for the record, that you can be properly blamed for it. Can you give us that explanation again?
Well, it was simply that you don't get many induced overvoltages higher than 300 kV. The most common disturbances in a distribution line are from nearby lightning, not from direct strikes. And so the nearby strikes induce a voltage whose amplitude depends how close and how severe the strike. And it was very, very rare to have anything above about 250 kilovolts. So we suggested then not to over-insulate a line, because the tendency in earlier times was to have much higher levels of insulation. And we said it's enough to be around 250 kilovolts. And at that time, Eskom increased that with a safety margin to 300.
In fact, it turns out that it's almost like more than 100% safety margin if you really look at it carefully and the data and so on. Be that as it may, that introduced a new problem, and that was wood pole splitting, and in the life cycle cost of it on a wooden pole, that eventually starts rotting of the pole, etc., etc. So you guys introduced a new problem. And the next generation, which comprises of people like Dr. Andreas Beutel, has tackled these problems. And at the same time, problems around bird electrocutions on MV lines, pole-top fires on MV lines, and a lot of other work has been done in the last years since this document was produced. And I've said to Andreas that it's time that the SAIEE organizes an international event, or an event with a very strong international flavor, because the work that continued around the subject in the South African environment is a substantial body of knowledge, and it's worth sharing it on an international platform. And as soon as COVID is kind of out of the way, we would like to go there. Andreas, the next slide, please.
Okay, this was you could say, the culmination of a lot of the research that was being done at that time in the CSR electrical engineering. It was also the time when Eskom was moving toward its 800 kV transmission systems, and we succeeded in getting a budget to set up a really high voltage research laboratory. The left hand is a diagram showing the layout of the outdoor laboratory with some of the big equipment. In the top right hand corner, you can see 3.3 megavolt impulse generator. That's the column in the right hand photograph with the high voltage screening electrode around it. And in this laboratory, we were able to go down scale from lightning strikes to studying long sparks, because we had 3.3 megavolt impulse capability, and we had 1 megavolt AC capability, with the transformers shown in the lower part of the diagram on the left. And so we were able to do some important measurements on long sparks here, under the altitude conditions of 1450, 1500 meters, because the air density correction factors were not very well known at that time for engineering applications. And Henry and his team also extended this into some studies of long spark physics and photographing the leader and streamer development in the long spark. So it was a nice consolidation between the lightning studies and the applications into engineering design for very high voltage and how the physics of that works. So maybe let's
Andreas,
go to
can you
keep the time.
Yes. We would like to wrap up now. Andrew, if you can, with the next 2 slides, wrap up for us.
Okay. Let's have the next slide. Yeah, that is what I said. This is a photograph of a long spark, 4 meter gap, and it shows the intersection between a leader coming down from a rod at the top and a streamer coming from a rod at the bottom. And it's very similar to the final stages of a lightning strike. The physics is essentially the same, just on a different scale. And what's important on the right, far right, is data showing the correlation between the length of that leader and the charge being lowered in the leader. And this whole lightning protection community that's involved in this charter and developing lightning protection application, I would like to remind you all that the lightning striking process is a charge-driven process. And the decision to strike or not has to do with the charge that the leader coming down is lowering from the cloud and how close that charge is brought towards structures, buildings, people, trees, and how that charge is distributed along the leader, because it is that charge that determines that decision process. And it's also the charge that is raised in the leader from whatever structure is going to be struck. Most lightning engineering talks about lightning current and protection, and it's actually the charge in the leader that determines that mechanism and how it strikes. And it's very difficult to correlate between current and charge because there's huge variation in the statistics, but that's a detail. But this kind of information is what finally found itself into modern installation coordination practice, bridging knowledge between long spark behavior, long spark studies, the physics, and lightning studies, lightning measurements. So it was a very satisfactory way to wrap up some of the work done at the CSR before it changed its strategic direction. So
Excellent.
We can close there.
Andrew, it has been exceptionally interesting and entertaining to listen to you. Thank you very much for sharing with us the early days of lightning research. Andreas, thank you for the opportunity. We hand it back to you.
Thank you, both Henry and Andrew, for a fascinating presentation and for doing it in such an engaging and interesting way. It was really fascinating to sit here and listen to. And I see there have been a few questions as well. If there are more questions, please ask them. There's still time to type them into the box. Right, thank you for that. And now for our second, well, third speaker, whichever way you look at it, looking at what is happening in the present and what we can look forward to with respect to lightning protection in this country, or lightning research in this country. I would like to say a big thank you to Professor Ian Jandrell from Wits University, where he is the Dean of the Faculty of Engineering and the Built Environment, and also a professor in the School of Electrical and Information Engineering. He is registered both locally and internationally as a professional engineer, and has received numerous awards over the years. In 2018, he was firstly appointed to the Sibanye-Stillwater Global Safe Production Advisory Panel. And also in 2018, he was honored to receive the NSTF South 32 Individual Award for Engineering Research Capacity Development. He is a widely published scientific author and has been a rated scientist with the NRF for more than 25 years. He received 2 awards from the SAIEE, firstly the Engineer of the Year Award in 1994, and secondly the President's Award in 2011. And over the past 25 years, Ian has supervised many postgrad students to completion, and he regularly mentors young engineers working in the industry, as well as he has also led numerous accreditation teams to other universities. Ian, it's a great pleasure to have you here, and I look forward to your presentation.
Andreas, thank you very, very much. Can I just check that the presentation now appears in front of everybody?
Yes.
Wonderful. So thank you. And I am going to speak about lightning research in South Africa, but obviously the overriding sort of thing that goes through my mind right now is, how do you follow an act like that one? If you wanted to launch your chapter with a big bang, quite frankly, I think you've had it. And I want to thank those 2 gentlemen very, very much for a really delightful presentation. I'm also mindful of time, so what I'm going to do is really try and go through a couple of key pointers, and also I don't want to take away from some of the things that people are going to hear about tomorrow. But I thought it would be interesting just to reflect for a little bit on what is it that makes lightning so very, very attractive. And I think the first thing to point out is that it's terrifying. You know, it can kill, it can damage, it can injure, and it often does that. And that's one of the most overwhelming things for a human being to think about. This is a force of nature that can be remarkably dangerous. Of course, we can control it. The other interesting thing is the stuff of myth and legend. And this is fascinating, because whichever culture you visit or look to, you will find myth and legend around lightning and the power that is lightning and thunder. It informs music, poetry, and art. It has fascinated people, I imagine, since it was first witnessed. And I've often reflected with the likes of Lee Berger, who is dealing with all these little hominids that used to live around this part of the planet. I imagine these folk running around looking at lightning events. So I think it's natural that it attracts researchers. And I'll say a little bit more about why individuals also attract people to lightning research. And then, of course, it's been formally researched in this country for decades. The Bernard Price Institute, the CSIR, at Eskom, and at universities. But there's another important point that I'd like us to pause for just for a moment. And that is that when I was putting together this presentation, I was really going to focus almost exclusively on the technical work that's taking place and the plans that we have for the future. And I'm going to say a little bit about that. But the interesting thing for me is when we ran a jam session last week, and Henry, I'm going to have to say this, to actually practice how we would make these presentations run smoothly, I engaged with yourself and Andy Erickson and with Andreas and other people in the meeting. And what hit me like a ton of bricks, and it's a story that both of you have shared tonight, is that this research agenda in lightning, in particular in this country, has really been made up by the people that made it real. I grew up doing postgrad work, reading papers by Anderson and Erickson. This was what I was brought up on in terms of what do you do about protecting a transmission line. I then ended up as a postgrad student working, and Henry, you may remember this, working at the CSIR for a while, led by this fellow called Dr. Henry Feldenes. And it's interesting how these little relationships form and actually start playing in your mind in terms of the direction that your career will one day take. And so what for me is profound is the collegiality of this environment. And it is the stuff of myth and legend. And my argument is the 2 of the folk that we've just listened to, they are the myth and legend that really make up this profession and this academic endeavor. And I want to really say this to all the younger people listening, and looking at Henry and Andy, I must say I'm much younger than both of them, and they won't disagree with this. But I'm really hoping that most of the people in the audience are younger than all of us. And I cannot think of a more challenging, welcoming, and rewarding environment in which to grow as a researcher than the one that has been really put together by the icons of lightning research, not only in South Africa, but internationally. And I'm aware that there are many folk from an international audience also listening tonight, and I really thank them for that. I want to just go back and sort of have a look at some of the things that we think about in terms of lightning. This is the most beautiful picture taken by a gentleman called Dave Mackay, looking at actually lightning over Devil's Peak in May 2009. And one of the reasons that we have this photograph was really back in 2009, we were looking to bring the International Symposium on High Voltage Engineering into South Africa, and we did that in Cape Town. And here to welcome people was this incredible photograph taken of lightning. And I think the other important thing is just to remember what makes it so very, very interesting to us. And if you look at this picture, I think you may be able to see my cursor. There are all these interesting phenomena. You can see the way this event or this phenomena branches downwards, telling us that it's negative downward lightning. You can see these sections where there's, it almost looks like lightning going back on itself. And of course, what you're looking at is that three-dimensional element. It makes one ask the question, to what extent does this event or this phenomena move horizontally from the point of origin in the cloud to the point of strike, in many cases on the ground? You see that it sometimes, if you look at this, even though this is a long exposure, it looks as though in the same flash, there may be more than one point of strike onto the surface of the earth. And of course, there are many strokes within that flash. And all of these things fascinate researchers and have really driven the research that we've done. The other important thing is to talk about the myth and the legend. On the right-hand side, you see the lightning bird, very common in mythology in Southern Africa in terms of this is the bird that lays the eggs that generates the lightning strike. You'll find this mythology in most cultures around the world. On the left-hand side, you have my little statue of Thor. This is the man who hits his hammer together, makes the thunder and makes the lightning, and that's what people grow up understanding. So the mythology and the legend around lightning goes back to time immemorial. The one important point I do want to make, and it's been part of the research that has been taking place in South Africa, is you've got to understand the mythology around lightning. You've got to realize that there's not just a scientific way of looking at things. There's another way of looking at things, and very often these things meet beautifully together. Then I want to talk about more myths and legends very briefly. Some of them you've heard about. The first one is, of course, Basil Schonland. In many respects, one of the first and most iconic storm chasers, ran around really fascinated by the lightning events in the Gauteng Highveld area. Then there was Dave Malan. Dave Malan, one of the first people to really get the photography of lightning to happen, to try and trace the way this mechanism formed. A bad picture of Dave Proctor, and I apologize for that. I edited it in at the last moment. Dave was one of the first folk who really looked at the radiation coming from a lightning strike to try and help us identify where was that storm activity. Can we triangulate and identify where lightning was occurring? And then you have Ralph Anderson, whom you've heard about. But Ralph was one of those people who many, many years ago when I was a young researcher, sat down with me and we'd share, it's true, and I heard the comment, we'd have beers together and we ended up writing, I think, a really nice paper together. And he had no problem in working with somebody like myself, who was so much younger and inexperienced. It was an absolutely wonderful experience. And then, of course, we have Andy Erickson, and I chose a much younger picture of Andy. I thought I'd be a little bit kind here. But this picture shows Andy receiving the Herman Halperin Award from the IEEE. And the reason I liked the full picture was that I had the privilege of serving on the Herman Halperin Committee for a 3-year period. That's the period you serve for. And I want to emphasize, of course, I wasn't on the committee that made this particular award. And then another young picture, of course, is Henry Geldenhuys, whom you've also heard about tonight. But what's interesting to me is you're looking at pictures of people, and it's these people who inspired other people to become interested in the field of lightning and lightning protection work. I want to emphasize to all the young researchers listening, all the young engineers listening, all the young people listening, that never underestimate the power of mentorship. People who actually care about what you're doing and want to enthuse you. That, I can assure you, is how my career got going. So the key point here is that many other people, I believe, can form part of this illustrious collective. In the current context for research, well, it's interesting that in South Africa, we've got a number of universities that are currently active. Wits University, Pretoria, UKZN, and University of Stellenbosch. Wits University, I think, has probably got the largest core of the lightning protection group, and I'll say a little bit more about that later on. The University of Pretoria is particularly well known for their work in forensic pathology, and in particular understanding the injury mechanisms of lightning. At Wits, we understand lightning and we try to protect against it. At Pretoria, they deal with the fact that it doesn't always work. And Ryan Blumenthal, who I'll introduce you to later on, has really been driving that agenda in terms of trying to really quantify and pin down all the injuries and all the deaths due to lightning. At UKZN at the moment, they've got a particular project running on how do you take rural communities and really advise them of the presence of a storm, warn them, and make sure that folk in those environments are safe. And at the University of Stellenbosch, they've had a project running looking, for example, at the influence of lightning strikes on, in particular, photovoltaic systems. And then, of course, you've got Eskom, the Weather Service, and various industrial partners that we, in fact, all work with. And I think some of the key points that one can make about lightning research in South Africa going forward is we know that without working with industrial partners from the university perspective, Eskom is one, but there are many other private companies out there with whom we now work, and we rely on them for the kind of support that sees research happening. And of course, the weather services, I'll say a little bit more about that later on. And South Africa has actually always been very active in lightning protection. And lest anybody forget, SABS 03, the original document on lightning protection, was quite frankly one of the leading documents of its day. We've now, of course, adopted the IEC standards, but SABS 03 was informed by the kind of information you heard Henry and Andrew talking about earlier on. It was an iconic document and always will be. And then if we were to say, what is it that drives research in South Africa at the moment? It's simple. To find better ways of protecting living beings and systems. How do we do that? Well, some of it is obvious. We've got to understand the phenomenon itself. And although we know a lot about that phenomenon, you will hear, particularly tomorrow, that we continue to learn more and more and more about this phenomena almost on a daily basis. And this just blows my mind. We're learning more about lightning as a phenomena all the time. Then we want to understand the risk. So we really need to quantify the risk of lightning causing damage or industry. And once again, we thought we knew a lot. There's a lot more to be discovered. We want to model system performance better, and we want to optimize protection strategies. And those are the four pillars around which current research is really being built. If you want to understand the risk, well, you heard about the ground flash density and that absolutely iconic CSIR ground flash density map. Then many would remember that Eskom installed the lightning positioning and tracking system, and then the Weather Services more recently has installed the South African Lightning Detection Network. And in fact, the Lightning Detection Network allows us to really identify and measure and quantify, say intelligent things about a large proportion of the lightning flashes around the Southern African region. And there's a lot of work that needs to be done in terms of, again, understanding the accuracy, understanding how we should interpret and use that data. And then, of course, the other point that's emerging from that is doing more and more work around looking at the number of strokes per flash. How many strokes per flash are there? And how many points of strike to the ground are there per flash? And once again, we may have an intuitive understanding, but the combination of the work being done, certainly at the University of the Witwatersrand, and we'll speak about that in a second, with the weather services and their data, is allowing us to actually quantify these numbers far more accurately than we ever did in the past. And then there are a number of local risk factors, which I think from an industrial point of view, make lightning protection and really understanding lightning protection particularly interesting in this context. But that I know is those local risk factors I know will be part of a presentation tomorrow, so I'm not going to say too much about that. All I want to emphasize is that we've got pretty dry conditions, so poor soil conditions, and we've got fairly high densities of population and industry where we have high ground flash densities. And these combined mean that we cannot back off on lightning research in South Africa. In terms of modeling system performance, the earth electrode performance, a lot of work has been done on the footing resistance and the behavior, and then importantly, soil ionization. And here I think about work, for instance, of Elsie Utley, who many of you would know, and even Professor Ken Nixon looking at soil ionization and understanding that in the South African context, the ionization within the soil profoundly impacts on the behavior of an earth electrode system. And it sounds peculiar, but almost there's a case to be made for if you are able to drive an earth electrode into the ionization phase, you can drop that resistance quite substantially and you get better system performance. And then the whole issue of equipotentialization. The important thing about earthing and lightning protection is that traditionally, it's always been thought of as something that's in place to deal with 50 Hertz systems, and that is important. But the interesting thing then becomes what happens under high frequency conditions. And this whole concept of equipotentialization has been developed quite substantially in research work in this country. But the role of an Earth electrode, not just as a connection into the body of the Earth, but what is the role of the Earth electrode in a site-wide environment in terms of trying to form some part of an equipotentializing platform, equalizing potentials across a network or a system during lightning strikes? And in fact, just going back to that one, it was really looking at the issue of soil ionization and the role of an Earth electrode as part of a bonding network that ended up seeing a fellow, all very well known to all of you, Professor John Van Coller, and myself end up at the International Conference on Lightning Protection for the first time that we'd ever been there in 1992. And you heard Henry's comment about the 1998 conference. In 1992 in Berlin, myself and John arrived there with a model of what happens to a building Earth electrode under transient conditions and looking at the role of an interconnected building earthing system, because we'd realized that in the South African context, this had become completely critical. And then surge protection obviously has driven a lot of the research. And in fact, there are a number of patents that have been filed outside of South Africa. But once again, it's getting surge protection to really, really work in the context of a lightning protection system that has been the driver of research. Then in terms of optimizing protection strategies, there are three key elements. The first one is safety, living beings and systems, but of course, safety first, and something that you'll hear about more tomorrow as well. And then the protection of transmission and distribution networks. You've heard the comments made by our two colleagues previously, really absolutely seminal work on that 10 kilometer long 11 kV line in terms of really looking at the attractive radius of structures and understanding protection. And Eskom has been continuing along this substantially. And then I think one of the most profound areas of research is looking at the concept of lightning protection systems. A lightning protection system isn't an Earth electrode. It isn't external lightning protection system. It isn't just using natural components. It isn't just having additional components added to structures. It's how you consciously combine all of these systems together to make a lightning protection system that really works in the context of the system you're trying to protect. This implies that the lightning protection system in the modern world has to include the external lightning protection system and the internal lightning protection system. And these systems have to work together if you're going to have success. How many times has one seen massive failures? And I suppose maybe people like myself get involved when things have gone wrong. Massive failures where there's been a lot of money invested in a lightning protection system, but nothing's been done in terms of the internal protection system. Or a lot of money's been put into the internal protection system, but nothing's been put into the external protection system. It's how you combine these things appropriately that make all the difference. Then in terms of human safety, there's a lot we can say, but a lot of work's been done in this area. Looking at the injury mechanisms, we know that there were 4 injury mechanisms, and now there are many more. We've developed a 5th and 6th mechanism. International researchers have been working at this for a long, long time. And if Professor Mary Ann Cooper is listening, she would have been recognized that one of the first people working in this area was in fact herself. And I'll say a little bit more about that. But the other element is, of course, this forensic pathology and lightning medicine, a discipline called lightning medicine, where we try to understand the injury mechanisms, really understand what do we do when somebody's been injured or has died. What does this tell us about lightning protection? And I just do have to do this because way back when, I had the absolute privilege of writing a paper on the 5th mechanism with Ralph Anderson. And many of you will remember, this is a paper that went back to the Morocco Swallows Jomo Cosmos match. I think it's the George Goff Stadium in 1998, and it was during a thunderstorm. And the interesting thing was this particular event, shocking though it was, allowed us to really find clear evidence of the 5th mechanism of lightning injury. And we can see from the imagery and by going through the video presentation that the strike actually occurred to the seating. And if you look at this still, and this was a really difficult piece of work to do, these are still frames out of SABC tapes at the time. If you look at this picture, you will probably be able to see over there, there's just a little cloud of dust. So we know that the lightning strike was actually not to the field, but was actually to the stand, and there was a little puff of dust there. The interesting thing was the injuries were quantified. The team doctor, Dr. Nematswarani, Humbulani Namatswarani, who literally lives next door to me now, was on the field, did a lot of the assessment of the players. We know what the injuries were. Players were on one foot, players were airborne, and these people had very severe injuries. And what this showed us was the following, that the fifth mechanism spoke about the launch of the upward leader, the upward streamer, from players on the ground, whether they had one foot on the ground or whether they were airborne, during the approach of the downward leader. And once the strike has occurred, that upward leader which left from players on the ground had to recollapse back through their bodies, and that was sufficient to fibrillate the hearts of these players. And then we go to forensic pathology and the sixth mechanism, which was barotrauma. And here's a picture of my dear colleague, Ryan Blumenthal from the University of Pretoria. And of course, Ryan, he likes to cut to the chase, as it were, and has even written a book on the role of a forensic pathologist in South Africa. But Ryan worked very closely with us in terms of understanding not just the fifth mechanism, but the barotrauma, the blast effect caused by lightning, and the likelihood of that effect causing injury to people and living systems. Then going back to protection and human safety, it's interesting that many policies have been developed. And I think I put this in particularly for the benefit of Dr. Henry Geldenhuys, who will understand my motivation. We've been involved, for example, in developing the guidelines for South African rugby. And many people will be angry that at the real moment when your favorite team is just beginning to look good, the players are cleared off the team because of a lightning warning. And there's a clear policy in place, and the policy is in place to protect the lives of people. It is not to necessarily make an audience on a television system happy. It's to protect the lives of people. And then the other point that I just want to emphasize a little bit, and you'll hear more tomorrow, is this lightning protection is a subset of human safety. You see, it's not just about the protection. I've had people injured on my plant, and I had a lightning protection system in place. One real event was folk who had to go up large smokestacks to measure gases being discharged from a plant, and they would have to make these measurements at certain times, whether or not there was a thunderstorm. So the key thing is to remember that it's lightning safety first, and your lightning safety plan, and it sounds so obvious, but really it's hard to implement in many industrial environments. Your lightning safety plan comes first, and you follow that up with a lightning protection strategy. And the other interesting thing is it's how you ask people to behave in a storm. It's not just what you ask them to do, it's how you ask them to do it. So for instance, if you're dealing with folk who honestly believe that in a thunderstorm you have to cover the mirrors, because if you don't cover the mirrors, you will have a lightning strike. Well, you encourage them to do that, but also make sure that they do a number of other things which will protect them in the case of a lightning storm. Much work is being taken place at schools, at many events, and looking at rural activities. And many of the colleagues that you will hear from tomorrow and whose pictures I will put up later on have been involved in many of these interventions to try and make sure that lightning protection, lightning safety, and lightning itself isn't just something which is frightening. It's something which we understand must be treated with respect, but it's something that we can actually protect against and mitigate the bad effects of. Looking at transmission and distribution networks, this whole concept that you've heard about shielding, earthing, and surge protection, you've heard a lot about that already. And then, of course, the issue of what is the appropriate rating for a surge arrestor? One needs to decide that in the context of distribution networks. And then what are those benefits of shield wires, even when they're not used for direct strikes? In many cases, your shield wire will take a direct strike and still flash over. It's the business of actually reducing the electric fields and really understanding that phenomena. And then you heard about this, the use of wood poles. And interesting, Andreas, I'm looking to yourself, the use of a wood pole almost as a surge arrestor in the context of a distribution network. And then storm tracking and response. Really making sure that we are really monitoring the movement of storms across the country, how they will impact on our transmission networks, and having teams ready to deal with the effect. And then the close South African Weather Service and Eskom interactions. I think these are one of the most effective proactive mechanisms to ensure that lightning protection and identifying where the risk is the highest have really benefited. From the lightning protection system. Looking at the lightning protection system, we've got many unique South African challenges. The overnight corrosion problem, which isn't really unique to South Africa. You've got copper electrodes and copper conductors, and in the period of 24 hours, sometimes they corrode, or at least they vanish. The use of natural components, how we optimize the use of natural components in structures, rather than having to rely on additional components. This question of integrating the external and the internal lightning protection system, looking at surge protective device zoning, really understanding the zoning mechanisms to ensure that your electronic systems and your more sensitive systems are adequately protected. And then looking at wind and solar, and understanding that these new systems have got challenges all of their own. You've got the rotor blades of the wind energy systems, which you've got to pay attention to. And in terms of the solar plants, kilometers by kilometers of photovoltaic systems. And to understand the impact of lightning on those plants, to understand the impact of multiple strokes on those plants, to understand the fact that you may have a strike to one part of that plant, and very, very easily you could cause damage to other parts of that plant simply because you've allowed surges to travel into that environment. So these are areas which have got a lot of focus in terms of understanding optimal protection systems. Screening, shielding and bonding, cabling strategies, and a lot of the big surprises over the years in terms of understanding what do you do with that screen? How do you protect against a magnetic field? Andy Erickson mentioned that there's charge in the process. When that charge becomes a current flowing in a conductor, you generate magnetic fields. How do you protect against that? And there's a lot of work that's been done in that. Then finally, lightning physics and behavior. Just to say a little bit about the future, because I do take note of the time. One of the things that you will hear about tomorrow is this massive move into high-speed photography, the capacity to not only photograph lightning strikes, but to actually photograph the development of the lightning strike itself, to look at the discharge formation, the movement of the leader from the cloud to the ground or vice versa, and to see how this process develops its own channel and ultimately ends up striking the ground. You'll hear a lot more from that from Dr. Hugh Hunt, who's working with Dr. Karina Schumann in terms of some of the most remarkable photography and research around this behavior. Then we have this direct measurement of current. You heard about the CSIR mast. You've heard about many other instances where there was direct measurement of lightning current. But now what this team is doing is looking at if we can measure the direct current, not the direct current, measure the current into a structure, simultaneously photograph that using high-speed photography, and also use the South African Lightning Detection Network to tell us everything we know about that particular strike. Then we start talking about really good information. And that has led to the formation of the Joburg Lightning Research Laboratory, the JLRL. You're going to hear a lot more about that, but this is an outdoor research laboratory. It's real, it's exciting. And in my view, it's the kind of research and output that actually deserves to be counted. And you will hear about that tomorrow. But this combination of really, really good photography which I imagine folk from 10, 20, 30 years ago would have dreamt of happening, which allows us to see that formation, to watch it strike, to measure the current flowing through the structure, to see what the detection network is telling us about that particular strike. Now, this is the kind of stuff which is going to really feed into the future of lightning research in South Africa. And then finally, I just chose to put on the screen some of our colleagues in the permanent staff in the Lightning Protection and Lightning Research Group, Lightning EMC Research Group at Wits University. And I recognize colleagues at other universities as well. But here we have people who form the core of that group. They're permanent staff members. On the top left, Professor Chandima Gomez, Professor John Van Coller, Professor Ken Nixon, Dr. Hugh Hunt, and Dr. Karina Schumann. We note, of course, that these people who only have doctorates at the moment are obviously working towards their professorships, hopefully faster than slower. And Chandima, I need to recognize the fact that you've joined our group after you and I have known each other for decades. And it's fantastic to see the energy that you brought into this group. And again, I want to end this slide with the following, and that is that anyone out there listening could well become part of this group and contribute to the future generation of knowledge in the area of lightning and lightning protection. And then I mentioned right in the beginning that in 1992, myself and John Van Coller ended up at the International Conference on Lightning Protection in Berlin. And it was interesting because the wall had just come down and it was a fascinating place to visit. But what I can tell you is that it's an absolute pleasure to be able to say that in 2022, the 36th International Conference on Lightning Protection is going to be coming to Cape Town. We are, to be honest with you, really confident that it will be coming to Cape Town and it won't just be in a virtual mode. There's a lot of information on this slide, but I put up two names. The technical session chair is Dr. Hugh Hunt, whom you will be interacting with substantially during the course of tomorrow. And the partnership chair is Professor Chandima Gomez, who's, I know, actively involved in the SAIE and this particular chapter. I want to conclude this presentation by once again just saying, Andreas, Dr. Beutel, to congratulate you and the SAIE, Professor Maharaj, Sunil, if you're still there, to really recognize that I think it's fantastic that the SAIE has recognized the value of having a chapter that looks at lightning and lightning protection, and to provide, I suppose, a technical and research home for many of us who find this to be an absolutely fascinating area of research. With that said, I thank you.
Thank you, Ian, for another fascinating presentation as well. And I really appreciate the time and the effort put in by all three presenters in compiling presentations that, I stand corrected, but were in the large part compiled especially for this evening, especially the first presentation. And I really appreciate it, and I'm sure everybody who has been attending appreciates it too. Before we get into questions, I'm going to try and pull up my camera again. I've had a power failure here where I am, so I've got a bit of a background. There we go, that doesn't look too bad. Bit of a darker background, but that seems to be fine. It's not Eskom, by the way. So in fairness, we're going to start with the questions at the beginning, or the ones that were asked first, and then move on as we go. If we run out of time, as I said, we will try and answer the ones that we miss by email. Okay, the first question says, and that's to Andrew Erickson, thank you. It's nice to know who the questions are for. What was the spacing between the field mill and the tower to ensure that the field mill was not affected by field enhancement due to the tower?
We didn't pay a lot of attention to this because we weren't trying to measure the absolute field. We only wanted to measure relative fields. But in the early days of the tower project, we had several field mills around, some of which were up to half a kilometer away, and others which were within about 20 to 20 meters of the base of the tower. Shall I go straight on to the next one?
Yes, please. You can read.
The test line was not floating. It was a practical line. It was energized. There were transformers on it, generator providing the power. At various stages of the project, there were surge arresters on it. The currents were measured at the base of the surge arresters. And in Henry's stage of the project, which went much further, a number of practical applications were investigated. A surge arrestor would theoretically and in practice influence the induced voltage only in that it clearly discharges the voltage once it reaches the surge arrestor. But of course, on a line like that, we could also measure the propagation of the surges along the line and see the difference between the middle of the line and the end of the line.
Andreas, if I might just add, a lot of that detail is reflected in some of the reports that's available, and if people are interested, I can make available the details behind that.
Thank you. I think I'm sure that will be of interest. The next question, I don't want to put anyone on the spot, but Ian, maybe that's one that you can take. I think your WITS colleagues have been working in that field.
This is the one about lightning warning technology. Absolutely. So the bottom line is that we do have access to that lightning data in real time in South Africa. So many of you, I mean, I have an app on my phone which will automatically warn me if lightning's within a certain distance so that I'm aware of that. The work I mentioned at UKZN was particularly in a rural environment where they were combining South African Weather Services information and handheld devices which allow one to detect the arrival of a storm. I think, Andreas, the one thing I must just say about this is that these technologies are all very, very important. One of the challenges that we've seen, and many of my colleagues will agree with this, is where you're dealing with environments where people have been injured. In many cases, they have these warning systems in place, or they have access to South African Weather Services data. But the interesting thing is people don't always take that particularly seriously. And in fact, folk are far more interested in getting back home or whatever it is, rather than understanding these warning systems are there to really help us keep ourselves safe. And I've always been amazed at how many times you see a failure of a warning system, and when you analyze what went wrong, everything was there. The warning was in place, but people didn't obey. And I think that's a message. Although the probability is very low, this probability is real, and those who have to deal with the aftermath of this will say, we must take this warning incredibly seriously.
Great, thank you for that. Can you move on to the next slide, please? There were more questions from what I remember. Oh, are those the only ones that made it onto the... Okay, let me see if I can read some of them out here then. One of the first questions we had was, which has been answered, I think, but just in case anybody else has the same question. If you are not a South African, I'm sure you can join. Please just join. If there are any problems, we can address those later. But it will be fantastic to have anybody wanting to, who's interested in lightning and would like to join, to please join. Then these ones we've seen. Okay, this one I think has been handled already, and that is it. I'll take back what I said. It's been a really fascinating and fantastic session, and I think our timing has been impeccable. Earlier, I sent messages through to Henry saying, please will you continue talking for a bit longer, because there were very few questions, but we got some good questions and comments coming through right at the end of that, and I appreciate the fact that Ian, you stuck to your time too, and you, as the last speaker, manfully accepted the fact that the last speaker usually starts late. But I really appreciate, again, the excellent presentations that we've had, the time and the effort that went into preparing them. And I repeat that, firstly, tomorrow we have another day. Again, same time, 5:30 to about 7:30. You saw the 3 speakers that we have tomorrow. Secondly, today's session was recorded and will be available through the usual SAIEE channels. And I really hope to see most, if not all of you, I say see in inverted commas, again tomorrow. Finally, again, just a big thank you to everyone, apart from the speakers, who has helped to make this session a success. All the backroom people, Hugh, Minks, Professor Ken Nixon, and my colleague, Nishal Mahato, who've been helping with the questions and all the logistics and everything as well. I wish everyone a safe and pleasant evening, and look forward to tomorrow. Goodbye and stay safe.